Good morning to everyone. I'm Dr. Sumi MS. The name of the course is Electromagnetic Fields, and today's lecture topic is Application of Gauss Law from Unit 2 Electrostatics. On completion, the students will be able to understand the different applications of Gauss Law, solve problems based on Gauss Law. Gauss law. Gauss law states that the total electric flux out of a closed surface equals to the charge contained inside the surface divided by its absolute permittivity. The electric flux in an area is defined as the electric field multiplied by the surface area projected in a plane perpendicular to the field. According to the Gauss law, the total flux linked with a closed surface is 1 by epsilon naught times the charge enclosed by the surface. For example, when a point charge q is placed inside a cube of edge A, then the flux through each face of the cube is given by q by 6 epsilon naught. Applications of Gauss law. Gauss law is used to make calculating the electric field easier. Few applications of Gauss law involve finding the electric field due to infinite straight wire, electric field due to infinite plane sheet, electric field due to thin spherical shell. Electric field due to infinite wire. Consider a wire that is infinitely long and has a linear charge density lambda. To compute the electric field, we utilize a cylindrical Gaussian surface. The flux through the end of the surface will be zero since the electric field E is radial. This is because the electric field and the area vector are perpendicular to each other. We may consider that the electric field's magnitude will be constant since it is perpendicular to every point on the curved surface. Given below is the diagram representing the electric field due to the infinitely charged wire. The curved cylindrical surface has a surface area of 2 pi r L and the electric flux flowing through the curve is given as E into 2 pi r L, and according to Gauss law the flux is given as Q by epsilon naught, that is E into 2 pi r L is equal to lambda L divided by epsilon r. Hence the electric field due to the infinite wire is given as E is equal to lambda divided by 2 pi epsilon naught r. It is important to note that if the linear charge density is positive, then the electric field is radially outward. If the linear charge density is negative, then it will be radially inward. Electric field due to infinite plane sheet. Consider an infinite plane sheet with a cross-sectional area A and surface charge density sigma. The electric field generated by an infinite charge sheet is perpendicular to the sheet's plane. Consider a cylindrical Gaussian surface whose axis is perpendicular to the sheet's plane, and as per Gauss law, we can calculate the electric field E as follows. And the flux is given as Q by epsilon naught, and charge Q will be the charge density sigma times the area A in continuous charge distribution. We consider electric flow from the two ends of the imagined Gaussian surface when discussing the net electric flux. The curved surface area and the electric field are perpendicular to each other, resulting in zero electric flux. And as a result, the net electric flux pi can be given as EA minus EA, which is equal to twice EA, where 2EA can be written as sigma into A by epsilon naught. Hence, the electric field due to the infinite plane sheet is given as E is equal to sigma by 2 epsilon naught. From the above formula, we can understand that the electric field generated by an infinite plane sheet is independent of the cross-sectional area A. Electric field due to thin spherical shell. Consider a thin spherical shell with a radius r, charge q, and a surface charge density of sigma, such that sigma is equal to q by 4 pi r square. The shell possesses spherical symmetry. The electric field owing to the spherical shell can be calculated in two ways: outside the spherical shell as well as inside the spherical shell. Electric field outside the spherical shell. Take a point P outside the spherical shell at a distance r from the center of the spherical shell to get the electric field. We use a Gaussian spherical surface with a radius of r and center O. Because all points are equally spaced or from the sphere's center, the Gaussian surface will pass through P and experience a constant electric field E all around. Therefore, the total electric flux pi is given as Q by epsilon naught, which is equal to E into 4 pi r square. Charge contained inside the surface Q is equal to sigma into 4 pi r square, and substituting we get E into 4 pi r square is equal to sigma into 4 pi r square by epsilon naught, and we can write the electric field as sigma r square divided by epsilon naught r square. Electric field can also be written in the form of charge as representing sigma is equal to Q by 4 pi r square, and the electric field outside the spherical shell can be written as E is equal to K into Q divided by r square. It is important to keep in mind that if the surface charge density sigma is negative, then the electric field will be radially inverse. Electric field inside the spherical shell. Let's look at a point P inside the spherical shell to see how the electric field is present there. We may use symmetry to create a spherical Gaussian surface that can pass through P and is centered at O and having a radius r. And based on Gauss law, we shall write the flux Q is equal to Q by epsilon naught, which is equal to E into 4 pi r square. Since the surface charge density is spread outside the surface, there is no charge contained inside the shell. Hence, Q can be considered as 0. Therefore, the electric field inside the shell from the above formula is also becoming 0. That is, E is equal to 0. Example programs on application of Gauss law. Example 1. A hemispherical ball of radius r is placed in a region of space with a uniform electric field E. Find out the electric flux through the ball. The surface area of the given ball dA is equal to 2 pi r square. The field lines are parallel to the axis of the plane of the ball, that is theta is equal to 0 degree. And the electric flux pi is given as E into dA cos theta. Substituting dA as 2 pi r square, we shall write and theta as 0, we shall get the electric flux as E into 2 pi r square. Hence the electric flux through the ball is given as E times 2 pi r square. Example 2. How does the electric flow via the Gaussian surface vary if the radius of the Gaussian surface containing a charge is half? Even when the radius is half, the total charge contained by the Gaussian surface stays the same. Hence, according to Gauss theory, total electric flux remains constant. The electric flux will not vary as it passes through the Gaussian surface. Example 3. A cylindrical surface of radius r and length L encloses a thin, straight, infinitely long conduction wire with charge density whose axis coincides with the surface. Find the formula for the electric flux through the cylinder's surface. A thin, straight, infinitely long wire has a uniform linear charge distribution. Consider the charge enclosed by the cylindrical surface to be Q, and the linear charge density lambda is given by Q by L. Therefore, charge enclosed by the surface can be written as Q is equal to L times lambda. The total electric flux through the surface of the cylinder pi is equal to Q by epsilon naught. Substituting the value of the charge Q as lambda L, we get pi is equal to lambda L by epsilon naught. Therefore, the formula for electric flux through the cylinder surface is given as lambda L by epsilon naught. Quiz questions on applications of Gauss law. List the applications of Gauss law. Determine the electric field due to infinite wire. Determine the electric field due to infinite plane sheet. Determine the electric field outside spherical shell. Determine the electric field inside spherical shell. How does the electric flow via the Gaussian surface vary if the radius of the Gaussian surface containing a charge is r. Thank you.